In this video, we will focus on size exclusion chromatography, which is mainly used to analyze aggregates and fragments in our protein samples. Okay, why do we need to analyze by size exclusion chromatography? In a protein sample, we typically have impurities, low molecular weight impurities and high molecular weight impurities that differ in size to our desired product, the monomer, and thus we use size exclusion chromatography to separate those. On the low molecular weight impurity side, we have fragmented proteins that may not be active anymore. They may come with increased immunogenicity and have altered pharmacokinetics, so all of which has an impact on function and safety, so we need to analyze those. On the high molecular weight impurity side, what we find is typically dimers or multimers, so any kind of aggregates of our desired protein, and also aggregation with some of the low molecular weight impurities. Again, we come across reduced activity and increased immunogenicity. But with size exclusion chromatography, we have a method on hand that is very gentle to separate those impurities, and it preserves the biological activity as we work in physiological conditions, meaning the pH, moderate salt concentrations. It's a non-adsorbing technique in comparison to other chromatography methods such as ion exchange, for instance, and we will come across low peak capacity, so we cannot load a lot onto the column, and furthermore we rather dilute our sample than concentrating it by the chromatography. Last but not least, we are dependent on the column length, the particle size, the flow rate, all of which we can use to later on improve our separation performance, as we will see. Okay, how does SEC perform the separation of differently sized molecules? We have a porous stationary phase, and the pores are very important as they determine in which molecular weight range I can separate my molecules. So the smaller molecules, they will enter the pores and will have a long way down to the end of the column and elute late, whereas the larger molecules that cannot enter the pores will go straightly through to the end of the column and therefore elute early. And this is what it looks like in a real-life example. We have our protein sample with low and high molecular weight impurities, as well as our desired product, the monomer. If we separate it on a size exclusion column, what we will get is the chromatogram with the high molecular weight impurities, such as aggregates and dimers, eluting first, then our monomer, and the latest will be our low molecular weight impurities, as those are the smallest. And we can determine the percentages, and typically this is something which is required for QC of a biotherapeutic protein-based product, as this needs to be within specific limits. Before we go into examples on how to improve the separation performance, I would like to quickly go into the theory of size exclusion chromatography, as this will help us understand why we can change specific things to make the separation better. And yes, we will see some equations, but I will explain it, so no worries. Let's start with something you may already know from your studies, lectures, which is called the Van Deemter plot. So the Van Deemter plot, one is shown here, displays the plate height, which correlates with the efficiency of a separation, meaning the lower the plate height, the more efficient will our separation be, and how this differs with increasing velocity or flow rate. And what we also see is already some graphs that are displayed here, and they represent the different terms of the Van Deemter equation, and those terms represent the influencing parameters that we have on the plate height. This is in green the eddy diffusion, in red the longitudinal diffusion, and in blue the mass transfer resistance. So all of these have an impact on the plate height and efficiency of our separation, but what do they actually describe? So the eddy diffusion describes the diffusion that we have because of molecules of the very same size taking different paths through our bed in the column. You may imagine one molecule may take a path directly in the middle of the column and therefore does not need a long time to get to the end of the column, whereas another molecule, even though it's exactly the same, it may take a different path, maybe to the side of the column, and therefore takes a slightly little bit longer, and therefore we have peak broadening and an impact on our separation efficiency. However, this eddy diffusion is completely independent from the flow rate and is rather related to the geometry and packing of our column. Then the longitudinal diffusion, in contrast, you see here in red that we have a big impact of the longitudinal diffusion by the flow rate, meaning a high flow rate. We have a positive impact on the plate height and the efficiency of our separation. So what does longitudinal diffusion describe? Longitudinal diffusion is the diffusion that we have in parallel to our column and to the flow, meaning diffusion, which typically occurs always, maybe a little more into the direction of the end of the column or to the beginning of the column, and therefore again we have peak broadening and a impact on our plate height. And you can imagine if we have a very high flow rate, this longitudinal diffusion decreases as simply we don't have so much time for diffusion to occur, and the molecules themselves, they are pushed to the end of the column at the very same time. Last but not least, mass transfer resistance. This also depends a lot on the velocity or flow rate that we apply, and the mass transfer resistance is the extra time that it takes for a molecule to enter the stationary phase, get out of the stationary phase, and through the stationary phase. And this mainly depends on the particle size, meaning with a lower particle size we have lower mass transfer resistance and a more efficient separation. And as we see here, the second influencing factor is the velocity or flow rate. As you can imagine, that the resistance is much higher the faster we want to pump our molecules through the column. For everyone for whom it was a little too theoretical now, here is a Van Deemter plot filled with real-life example. Again, we see the plate height and the flow rate in this case, and we analyze the monoclonal antibody on 4 different columns that only differ in the particle size, meaning from 2 up to 10 micrometers. What we see at first sight is that the lowest plate heights, meaning the most efficient separations, we will get with the smallest particle, and the largest particle gives the worst separation performance. Furthermore, we do see that the influence of the flow rate is bigger for larger particles than compared to smaller particles. Secondly, something that is very important for size exclusion chromatography, as we don't have an adsorption to the stationary phase, but actually what we use is the diffusion of the molecules in and out of the pores, is actually the size of the molecule. So here we had a monoclonal antibody, but if we talk about something which is double as big, like the dimer of an antibody, we have a change in diffusion. This means larger particles diffuse more slowly. And one impact that it has is that the influence of the fluid is even worse with larger molecules as compared to smaller molecules. This will be the last equation that we look at, and it describes how to calculate the resolution. The resolution tells us basically how well we can separate two adjacent peaks. And of course, what we need to know, and what we will also find in the formula for that, is how far they are separated. And this is done by just taking the difference in the retention time or the elution volume. Secondly, what has an impact is the width of the both peaks, because if we have very broad peaks, they may weld in together and we cannot separate them anymore. And this is exactly what we will find in the equation for the resolution calculation. So what we will get is a value, and these can tell us how well we have two peaks separated. So typically a value of 0.5 is not a very good separation of the two peaks, even though it may result in a double peak. Then a resolution of 1.5, we typically say it's a good separation and may also be a baseline separation. But I would like to hint to one phenomenon. That resolution numbers do not always tell us how well we see two different molecules in the SEC chromatogram. So this is something that we see, for instance, for a resolution of 0.6, which is rather low, but if we have a solution that contains a ratio 1:1 of two different molecules, we can still see that there are two different molecules in the solution. However, if we have one of the molecules only be in the solution at 1/16, we can hardly see that there are two molecules hidden in this peak. And of course, this is something that you would expect. With increasing resolution, we can still see two different peaks, even though we have one of the molecules only present at a very low concentration in our solution. In the next step, I would like to take what we just learned from the von Deemter and resolution calculations and see how we can actually apply that in a real-life example to improve our separations. First, we would like to look at how to improve the resolution. And one thing we just heard is that a reduced particle size has a lower mass transfer resistance, and therefore we will get lower plate heights and a higher number of theoretical plates in a column. And this is also something that we see in the chromatogram, which comes out of those columns. If we take a large particle size, we will have broader peaks and lower resolutions, whereas with a smaller particle size we will get sharper peaks and a better resolution. However, what we need to take into account is that we have an increase in the pressure drop, and our instrument needs to be fit for that. And this is what the difference in 2 micron particles and 5 micron particles in the separation of a monoclonal antibody looks like. What we see is on the one hand that we see more with the smaller particle size. In this case, for instance, we can see this little shoulder, and we can see on the low molecular weight impurity side this shoulder, which is not visible using a column with 5 micrometer particle size. Furthermore, what we can see is that we can reduce the analysis time using 2 micron particles instead of 5 micron particles. Another way to decrease the mass transfer resistance and thereby increase our separation performance is to reduce the flow rate. And this is what is shown here in a very drastic example, I need to admit, where we had one analysis running of a monoclonal antibody at, I would say, normal flow rate of 0.35 milliliters per minute. And then we switched to 0.05 milliliters per minute. It's probably not something you would do in a routine application, as it definitely increases the time the analysis takes. But to show the importance of the flow rate, this is quite a nice example. Because again, what we see is a better separation of impurities that were not visible with the higher flow rate. And this is also displayed in the resolutions that we get between peak 1 and 2, for instance, where we have a much better resolution here as compared to the high flow rate. And this is true for all the different separations of the different peaks. One thing we have not been talking about so far is how the length of the column influences our separation. As for size exclusion chromatography, we don't have any absorption, but we only have the molecules going in and out of the pores. You can imagine the more pores you can enter or not enter, the better will the separation be. And therefore a longer column actually also means a better separation. And this is what we see here. If we compare the separation on a 15 centimeter column of a monoclonal antibody, in this case, we can see the monomer and the dimer, and we also have a quite okay resolution between both, but clearly what we see on the 30 centimeter column is, for instance, here a peak on the low molecular weight side of the antibody, which is better separated as compared to the 15 centimeter column. I would still stick to the column itself and talk a little bit about the pore size and how to select the optimal pore size. So the pore size that you need to take is very much dependent on the molecular weight of the protein that you actually want to analyze. Meaning the bigger the protein, the bigger needs the pore size to be, or if you have smaller molecules, you can go for a small pore size. If we don't take the right pore size for the molecular weight range we want to cover, we may come across less resolution and lower separation performance. How we can see on the first side if we are in the right range with our column is calibration curves. So if you ever wondered why vendors offer those calibration curves to characterize their columns, it's to make it for you easier to select the right column. A calibration curve is basically a protein standard that contains proteins of different sizes. In this case, we start at 650 kilodaltons and we get down to around 40 kilodaltons, and there's also a small molecule with only a few daltons in this molecular weight standard. And then we run that on our column and plot the molecular weight against the retention time. What we get is such a curve. And what we typically see is on the high molecular weight side that we get a steep part. So we see it on those two columns, not on this purple one, which actually has the biggest pore size. And this means we do have a change in the molecular weight, but no change in the retention time, and thus no resolution. The same is true for the low molecular weight part, where we typically have a steep part, again meaning change in molecular weight but no change in retention time, meaning no separation in this case. And what we are actually looking for is a linear part of the column where we have a change in the molecular weight and in the retention time, meaning we can separate those molecules from each other. So if you know you would like to analyze a protein of 150 kilodalton, then you have a look, okay, which column is linear in that range. What we can see already, if we look at 3 different columns from 12.5 nanometer pores up to 30 nanometer pores, is that the small pores cannot separate our biggest proteins here, whereas the large pores columns can. And we do see that the low molecular proteins, they get closer together, meaning less separation in the low molecular weight range. Apart from the column itself, we have an influence of the HPLC system on our separation performance, and in particular the dead volume, meaning any additional volume between the injector and the detector that is not in the column, because there diffusion can happen, which leads to peak broadening and therefore decreased separation performance. And this is something that we tested on 3 different systems. An FPLC system with 200 microliter dead volume, HPLC system with 20 microliters dead volume, and a UHPLC system with 7 microliters of dead volume. We analyzed 2 samples, our protein standard that we already know, and a monoclonal antibody. And what we can see is, if we look here, for instance, in this region, we can separate with a lower dead volume this small shoulder, which is not possible on the FPLC system. Furthermore, we can already see that we have broader peaks in the FPLC system with a higher dead volume. And this also gets clear if we look at the plate numbers for the last peak, which is much higher for the UHPLC system as compared to the high dead volume FPLC system. Similar results we find for the monoclonal antibody. Again, better separation. In this case, we can see it clearly in this shoulder, and also higher plate numbers for the monomer of the monoclonal antibody. Next, I would like to talk about how we can improve our separation by using additives to our mobile phase. So one problem you may come across when using size exclusion chromatography is undesired interaction of our analyte with the stationary phase. Each vendor tries to minimize the secondary interactions as much as possible, but it's hardly impossible to get rid of them completely. So these interactions may be of electrostatic nature, meaning we have charged molecules that interact with our stationary phase, and to this end what we could do is increase the salt concentration and ionic strength of our mobile phase. Another type of secondary interactions may be of hydrophobic nature, meaning we have hydrophobic patterns on our proteins that interact with the stationary phase. And to this end, what is possible to add is additives such as organic modifiers that reduce this hydrophobic interaction. And what we see here is an example of a molecule, a antibody attached to a drug, meaning an antibody drug conjugate, and typically this drug makes the molecule more hydrophobic as compared to the antibody without the drug attached. And if we use our typical mobile phase containing 100 millimolar sodium sulfate, what we will see, this is shown here in blue, is that we have a bad separation of our low molecular weight impurities, and we also have a broad peak. Now, if we add, in this case, arginine to our mobile phase, we reduce these hydrophobic interactions, and what we see is, here in red, a better separation of our low molecular weight impurities, as well as a sharper peak. On this last slide, I would like to dip into a topic that we typically get questions on, which is the cleaning of SEC columns. So typically you have a reason why you want to clean your SEC column, because you see something is wrong. So this might be, for instance, a pressure increase, which might be related to a clogged thread. And in order to reverse that, we can basically turn the column and flush it in reverse flow to get rid of the clogged thread in the beginning of the column. Furthermore, what we might see is a decreased separation performance, meaning lower resolution, higher asymmetry, meaning tailings and frontings, higher peak width, and this may be due to adsorbed molecules. This can be of hydrophobic nature, and in order to flush those or to remove those from the column, we can either flush with 20% organic solvent solution of, for instance, isopropanol or acetonitrile, or the faster version, I would say, is to inject just 100 microliters of pure isopropanol or acetonitrile if the column stands it, and by that removing the adsorbed molecules. Another reason why molecules may absorb is electrostatic interactions. In order to get rid of those, we typically use a high salt concentration and flush with that. What we can also do is to decrease the pH and flush with such a solution so that the molecules that stick to our column, to the stationary phase, they will get positively charged, and if they interact by a negative charge, they will not interact afterwards anymore. Last but not least, what we may also find in particular after storage of the column is microbial contamination, meaning we see things, UV signals coming out of the column even though we did not even inject anything. And to this end, we can add sodium azide to the mobile phase, also to the storage buffer. For storing, what is another possibility is to store it in 20% ethanol, but again, this might not be applicable to all silica-based columns.